In May 1902, archaeologist Valerio Staes noticed something impossible looking inside a corroded mass of bronze recovered from the sea, the teeth of a gear wheel. The object had come from an ancient shipwreck off the small Greek island of Antikythera, but no known artifact from that period was supposed to contain a compact system of precision gears. At first, the fragments looked less like a machine than pieces of green stone fused with wood, sand, and salt. Yet beneath the corrosion were thin bronze plates, inscriptions, axles, pointers, and wheels whose tooth counts encoded relationships between the movements of the sun and moon. Today the object is usually called the Antikythera Mechanism. It is often described as the world's oldest known analog computer. That phrase is useful, but it can also mislead. This was not a digital machine, and it could not store software or make general decisions. It was a specialized calculating instrument. A user entered a date by turning an input, and carefully chosen gear ratios translated that motion into displays of astronomical cycles. In the language of mechanics, the machine embodied a mathematical model. The basic facts are remarkable enough without embellishment. The surviving mechanism consists of 82 fragments, including about 30 preserved bronze gears. Researchers estimate that only about 1/3 of the original device remains. Its wooden case was roughly the size of a small box or thick book. It was probably constructed in the 2nd century BCE and was already old when the ship carrying it sank in the 1st century BCE. But the central mystery is not simply that ancient Greeks understood gears. They had used toothed wheels in other machines. The mystery is how one workshop combined astronomy, mathematics, metalworking, inscriptions, nested dials, and more than 24 interacting gear wheels into a portable instrument of extraordinary density. What did the complete machine display? Who commissioned it? Where was it built? Did it represent a unique masterpiece, or one surviving example of a larger mechanical tradition that was later lost? And perhaps most importantly, how much of the device can modern researchers truly reconstruct from fragments that spent 2,000 years under the sea? The wreck that preserved a lost machine. The story began in 1900, when Greek sponge divers found a shipwreck near Antikythera while operating in dangerous waters between the Peloponnese and Crete. The wreck contained bronze and marble statues, ceramics, glassware, coins, furniture fittings, and luxury objects. It was not an ordinary coastal vessel carrying grain or building stone. Its cargo reflected the movement of wealth, art, and prestige through the late Hellenistic Mediterranean, when Roman collectors were acquiring Greek objects on an enormous scale. The divers worked in heavy canvas suits with metal helmets, connected to the surface by air hoses. At depths of roughly 45 to 60 meters, their time and movement were severely restricted. Decompression science was still poorly understood, and the recovery operation was dangerous. One diver died and others were seriously injured. Yet they brought up hundreds of objects during the first major underwater archaeological recovery in history. Among those objects was the unpromising bronze mass that later separated into fragments. The sea had both saved and destroyed it. On land, its bronze would probably have been melted down and reused, as happened to countless ancient statues and tools. Underwater, the device escaped recycling. But saltwater corroded the one metal, the wooden case decayed, gears shifted, and mineral deposits locked parts together. When the fragments dried after recovery, further cracking and separation occurred. This explains why the mechanism cannot simply be opened like a clock. It is not an intact machine waiting to be switched on. Its internal arrangement must be inferred from distorted plates, broken teeth, faint inscriptions, and X-ray images of components buried inside corrosion. The shipwreck gives the mechanism a latest possible date. Coins and other cargo suggest that the vessel went down during the 1st century BCE, commonly placed around the middle of that century. The machine itself appears older. Its lettering, astronomical design, and proposed calendar starting points have led different researchers to dates across the 2nd century BCE, with some arguments extending earlier. There is no single, universally accepted construction year. That uncertainty matters. It prevents a simple claim that one famous inventor made it at one known moment. The wreck tells us where the object ended its journey, not where it began. Antikythera is the name of the island near the disaster, not the known home of its maker. The vessel may have been traveling westward toward Italy. If so, the mechanism was moving through a world in which Greek scientific instruments could become trophies, teaching devices, elite possessions, or valuable cargo. But the identity of its owner and intended destination remain unknown. When the object refused to fit history, recognition did not immediately produce understanding. Early scholars proposed that the fragments belonged to an astrolabe or some form of astronomical clock. The problem was that the device seemed too complex for the accepted history of ancient technology. That assumption slowed interpretation because investigators were trying to identify the machine using categories already familiar to them. In the early 20th century, the German scholar Albert Rehm recognized that inscriptions and gearing pointed toward an astronomical calculating device. Decades later, science historian Derek de Sala Price made the mechanism central to his study of ancient technology. Using radiographs produced with Greek physicist Charalambos Karakalos, Price argued that it was a calendar computer driven by complex gear trains. His reconstruction was incomplete and some details were later replaced, but he established the essential point: this was not a decorative wheel or simple navigational instrument. It was a machine built to calculate cycles. The next decisive step came through imaging. Conventional X-rays revealed hidden gears, but overlapping metal made the interior difficult to interpret. In the 2000s, researchers used high-resolution surface imaging and microfocus X-ray computed tomography. Instead of looking through all the layers at once, CT scanning produced virtual slices through the fragments. Gear teeth could be counted more accurately. Previously, unreadable letters appeared inside the corroded material. The amount of deciphered text expanded dramatically. The inscriptions changed the investigation. They were not merely labels. Some described displays and astronomical periods, functioning almost like an engraved manual. Others named months, games, zodiac signs, and eclipse characteristics. Because much of the machine is missing, the words sometimes preserve functions for which no complete gear train survives. The result is a strange reversal. Researchers can be confident about some things the machine displayed even when the physical components responsible for those displays have disappeared. At the same time, surviving gears can be arranged in more than one plausible reconstruction when the supporting structure is lost. This is why every modern model must be separated into three categories. There are components physically preserved in the fragments. There are reconstructions strongly constrained by surviving gear counts and inscriptions. And there are elegant but more speculative solutions proposed to fill missing space. 2. The Antikythera mechanism is not a solved puzzle in the ordinary sense. It is a layered argument, with different levels of certainty. The back of the machine is understood far better than the front. Its solar and lunar functions are widely accepted. A planetary display is strongly supported by inscriptions, but the exact front gearing remains debated. What turning the handle actually did? Imagine the complete machine resting inside a wooden case. On the front is a circular display. On the back are two large spiral dials with smaller subsidiary indicators. A user rotates an input, perhaps a side-mounted knob or crank, to select a date. The machine does not observe the sky. It calculates what should appear in the sky, according to cycles built into its gear ratios. A simple pair of gears can multiply or divide rotation. If a wheel with 20 teeth drives one with 60, the second turns once for every 3 turns of the first. Combine many pairs and the resulting ratios can represent astronomical periods that would be difficult to track mentally. On the upper back dial, the mechanism represented the metonic cycle. 19 solar years are close to 235 lunar months. After that interval, lunar phases return to approximately the same dates in the solar year. The dial was arranged as a 5-turn spiral divided into 235 cells, each corresponding to a lunar month. A pointer followed the spiral as the mechanism advanced. The month names on this dial were a major clue. They belong to a Corinthian calendar tradition, linking the device culturally to Corinthian regions or colonies. Northwestern Greece and Syracuse in Sicily have both been considered. The inscriptions do not prove the workshop's location, but they make the calendar more specific than a generic Greek system. A smaller dial tracked a 4-year cycle associated with major Panhellenic athletic festivals. This feature connected celestial time with civic and religious life. The machine did not treat astronomy as an isolated science. Calendars determined festivals, public events, and the organization of communal life. The lower back spiral represented the Saros cycle of 223 lunar months, a little more than 18 years. After one Saros, the geometry of the Sun, Earth, and Moon returns to a similar arrangement, making eclipses recur in a recognizable pattern. Cells on the dial contained glyphs indicating predicted lunar or solar eclipses and information about their timing. A subsidiary Exeligmos dial provided a correction after 3 Saros cycles. A single Saros is not a whole number of days, so a repeated eclipse shifts by roughly 8 hours in local time. After 3 cycles, the accumulated shift approaches a full day. The machine encoded that correction mechanically. This is the first major payoff. The mechanism did not merely show where the moon might be tonight. It compressed decades of calendar and eclipse relationships into a hand-operated object. If you value documentaries that separate the surviving evidence from later imagination, this is a good point to subscribe. The Moon's imperfect motion in bronze. The Moon does not appear to move across the sky at a perfectly constant speed. Its orbit is not a centered circle, and its apparent motion accelerates and slows. A simple gear turning uniformly would fail to represent that variation. The Antikythera designer addressed this with one of the machine's most sophisticated surviving arrangements. A pin and slot mechanism combined with epicyclic gearing. One gear rotated around another while a pin moved inside a slot, producing a variable output. The resulting pointer could speed up and slow down over the course of a lunar cycle. 3. This is important because it shows the machine was not merely a calendar assembled from convenient integer ratios. It translated a geometrical astronomical theory into moving metal. The 2006 reconstruction linked this mechanism to the kind of lunar model associated with the 2nd century BCE astronomer Hipparchus, who worked on roads and developed quantitative methods for describing the moon's irregular motion. That connection is intellectually powerful but historically incomplete. The presence of a Hipparchan-style model does not prove Hipparchus designed the mechanism. Scientific ideas traveled. A craftsman could implement a theory developed elsewhere. The device may reflect a community of astronomers, mathematicians, engravers, and metalworkers rather than one celebrated genius. The front also displayed the phase of the moon, probably with a small rotating sphere showing light and dark hemispheres. As the mechanism advanced, the sphere turned to represent the changing illuminated portion, visible from Earth. The distinction between simulation and prediction matters here. The mechanism did not calculate from gravitational laws. Those laws would not exist for many centuries. It relied on periodic models derived from observed cycles and Greek geometrical astronomy, some of which incorporated numerical relationships known from Babylonian traditions. That combination is one reason the mechanism is historically significant. It is not evidence of a mysterious, isolated civilization with modern science. It is evidence of knowledge moving across cultures and being transformed. Babylonian eclipse cycles, Greek geometrical models, local calendars, festival schedules, and advanced craftsmanship were integrated inside one object. The machine therefore represents more than technical skill. It represents organization. Someone had to choose the astronomical parameters, convert them into gear ratios, plan the physical layout, cut hundreds of triangular teeth, engrave dense instructions, assemble concentric axles, and test whether the displays remained synchronized. A single brilliant idea would not be enough. The mechanism required a working tradition of precision practice. The dial that predicted darkness. Eclipse prediction is often described too dramatically. The mechanism could not determine whether clouds would cover the sky, and its dial did not generate a modern local forecast for every city. What it could do was identify months in a repeating cycle when solar or lunar eclipses were possible and provide encoded information about expected characteristics. The Saros dial is one of the strongest parts of the reconstruction because substantial pieces of its spiral and inscription survive. The eclipse glyphs include letters that correspond to explanatory text. Some indicate whether an eclipse was solar or lunar, while others relate to timing. The back cover inscriptions appear to have explained aspects of the display. To an ancient user, an eclipse was not just an abstract orbital event. It could carry political, religious, or astrological significance. Yet the evidence should be handled carefully. The mechanism's inscriptions mention eclipse features, including colors in some interpretations, but this does not mean the whole device was primarily an instrument of prophecy. Its construction is mathematical and calendrical, even if users lived in a culture that attached meanings to celestial events. The dial also reveals the difference between predicting a cycle and knowing the underlying physical cause. Babylonian astronomers had developed powerful arithmetic methods for recognizing eclipse recurrences. Greek thinkers debated the geometry of the heavens. The Antikythera Mechanism turned such periodic knowledge into a mechanical display. In 2024, researchers applied statistical methods used in gravitational wave analysis to a broken ring on the front of the mechanism. They examined the positions of surviving holes and estimated that the complete ring for most likely contained 354 or 355 divisions, strongly favoring a lunar year scale over proposed rings of 360 or 365 divisions under their model assumptions. This result is fascinating because it extracts information from damage itself. Only a small arc survives. The holes are distorted, incomplete, and affected by fractures. By modeling the likely original circle, researchers reconstructed a probable total that corresponds closely to 12 lunar months. But it is not the final word. The finding depends on measurements and statistical assumptions, and other. Researchers continue to propose different interpretations of the front calendar rings. The responsible conclusion is not that modern physics has completely solved the device. It is that new analytical tools can still recover meaningful structure from fragments studied for more than a century. The mechanism remains active science because every new reconstruction must satisfy several kinds of evidence at once. Tooth counts, available space, inscriptions, ancient astronomical periods, manufacturing tolerances, and the geometry of the surviving plates. The lost face of the cosmos. The greatest visual feature of the mechanism may be the part that is mostly gone. Inscriptions on the front cover describe the cycles of the 5 planets known in antiquity: Mercury, Venus, Mars, Jupiter, and Saturn. This strongly supports the conclusion that the front displayed a model of the visible cosmos, with indicators moving around the zodiac. The challenge is mechanical. The front would need multiple pointers rotating around the same center, each following a different non-uniform planetary cycle. Most of the gears required for such a system have not survived. Researchers must reconstruct them from inscriptions, a few unexplained fragments, known astronomical periods, and the limited depth of the original case. In 2021, a University College London team proposed a detailed model of the front cosmos. Their reconstruction used the planetary period relations preserved in the inscriptions and arranged complex gear trains to produce coaxial outputs for the planets, Sun, Moon, and lunar nodes. It was an ingenious attempt to make the words, tooth counts, and physical space agree. However, a successful modern model is not automatically a blueprint of the ancient original. Multiple gear arrangements can sometimes produce the same astronomical ratio. A reconstruction may be mathematically elegant while depending on gears or supports that are not preserved. Other researchers have questioned whether the device was a full mechanical planetarium in the form proposed, suggesting alternative roles for missing parts. This is where public presentations often become too certain. Images of a complete, polished reconstruction can create the impression that archaeologists found the machine intact and merely cleaned it. In reality, a reconstruction is a visible hypothesis. The back dials are anchored by extensive surviving evidence. The exact appearance and gearing of the front cosmos remain less secure. Even so, the inscriptions are difficult to explain if the planets were absent. They provide synodic period information, including sophisticated relationships for Venus and Saturn that are suitable for geared representation. The strongest current interpretation is that the front displayed planetary motions in some form, while the exact mechanism remains unresolved. The missing front also changes the meaning of the phrase ancient computer. The device was not only calculating dates. It may have presented an entire geocentric cosmos as a coordinated moving diagram. The Earth, according to the ancient model, remained at the center while indicators showed celestial bodies traveling through the zodiac. 5 for a student, patron, philosopher, or political elite, turning the handle would have made invisible mathematical cycles visible. The mechanism transformed the sky from a sequence of observations into a system that could be explored forward and backward in time. Who could have built it? No signature survives. No ancient text securely identifies this particular machine. That vacuum has attracted famous names, especially Archimedes and Hipparchus. Archimedes died in 212 BCE, probably before the surviving mechanism was built. Roman authors, including Cicero described mechanical celestial spheres associated with Archimedes and with the philosopher Posidonius. These accounts show that geared or moving astronomical models existed as a recognized category in antiquity. They do not prove that Archimedes designed the Antikythera Mechanism. The Corinthian month names have encouraged speculation about Syracuse, a Corinthian colony and the home of Archimedes. The lunar anomaly points toward astronomy associated with Hipparchus and Rhodes. The ship's route and cargo have generated additional proposals. None has produced a conclusive workshop. Location. The most cautious interpretation is also the most revealing. The mechanism probably emerged from a network, rather than from nowhere. Its maker inherited astronomical parameters, mathematical techniques, metalworking skills, and conventions for describing celestial cycles. Even if one designer coordinated the project, that person relied on accumulated knowledge. Why, then, has no second mechanism survived? Bronze was valuable and recyclable. Precision instruments were rare. Wood cases decayed. Thin plates corroded. Wars, shipwrecks, changing institutions, and the eventual decline of particular workshops could erase a tradition without erasing all references to it. The Antikythera device survived because it entered an unusual archaeological environment and was then recovered before the sea destroyed it completely. It is tempting to call it a technological object without ancestors or descendants. But that may confuse absence of surviving artifacts with absence of historical development. The literary references, the machine's internal consistency, and the depth of craftsmanship suggest that it was not a first attempt made by someone discovering every principle at once. At the same time, there is no evidence for factories producing such devices in large numbers. It may have been an elite commission at the extreme edge of what Hellenistic workshops could achieve. Its rarity may be real, even if its underlying tradition was broader. The unanswered identity of the maker is therefore not merely a missing name. It is a missing social world. We do not know how astronomers communicated with artisans, how gear ratios were planned, what tools were used to divide circles, how errors were corrected, how long construction took, or who could afford the final product. The object preserves the result, but almost none of the workshop around it. Could the machine really have worked? A reconstruction that turns smoothly on a modern display does not prove that the ancient device operated with equal reliability. Modern builders may use precise bearings, rigid supports, carefully corrected dimensions, and materials selected after studying the damage. The original used thin bronze gears with triangular teeth and hand-produced spacing. Mechanical studies have reached different conclusions about how serious these limitations were. Some analyses and physical reconstructions show that triangular teeth can transmit the modest forces required to 6 move pointers, particularly when the mechanism is turned slowly. Working models demonstrate that the fundamental gear arrangements are mechanically possible. A 2025 simulation raised a sharper question. It suggested that triangular tooth shape alone would create limited error, but that manufacturing inaccuracies of the size estimated from the damaged fragments could cause gear trains to jam or disengage. The authors were explicit about the uncertainty. Either the original machine may not have functioned as assumed, or the surviving fragments no longer preserve the original accuracy well enough to estimate it correctly. That caveat is crucial. 2,000 years of corrosion, crushing, mineral growth, recovery, drying, and cracking have altered the gears. Measuring the present eccentricity of a damaged wheel is not the same as measuring its condition when it left the workshop. There are several realistic possibilities. The mechanism may have worked but required slow, careful operation. It may have been adjusted by a knowledgeable user. Some supporting parts that reduced flexing may be missing. Its accuracy may have been sufficient for demonstration and calendrical calculation without meeting modern expectations of continuous clockwork. Or some reconstructions may place more gears under load than the original design did. The claim that it was merely a non-functional toy goes beyond the evidence. A device with extensive instructions, carefully encoded periods, eclipse glyphs, and coordinated dials would be an extraordinarily expensive way to create a static illusion. But the opposite claim, that every proposed planetary train certainly ran perfectly, is also stronger than the fragments allow. The best conclusion is mechanical, not mythical. The preserved device was designed as an operational calculator. Its exact performance, durability, and maintenance requirements remain uncertain. That uncertainty makes the artifact more human, not less impressive. The builder worked with tolerances, friction, wear, and error, just as every engineer does. What the fragments actually prove. The Antikythera Mechanism does not prove that ancient Greece possessed modern computers, electrical technology, or a forgotten industrial revolution. It does not require aliens, time travelers, or a civilization erased without trace. Those claims make the artifact less interesting by replacing documented ingenuity with fantasy. What it proves is more specific and more important. By the 2nd century BCE, at least one Greek-speaking workshop could construct a compact geared instrument that coordinated multiple astronomical and calendrical cycles. Its makers could cut fine bronze gears, arrange concentric motion, engrave technical instructions, model the moon's changing speed, represent a 19-year lunisolar calendar, track a 4-year festival cycle, and predict eclipse possibilities across a Saros sequence. The front probably displayed the Sun, Moon, and 5 known planets, though its precise gearing remains disputed. The confirmed mechanism is extraordinary. The unresolved mechanism is equally valuable. We still do not know its maker, workshop, owner, exact construction date, full planetary arrangement, complete operating method, or original level of accuracy. We do not know whether similar devices were common among a narrow scientific elite or whether this was an exceptional commission. The history of the investigation also carries a warning. Each generation reconstructed the machine using the best tools and assumptions available. Early visual inspection revealed inscriptions. Radiography exposed internal gears. CT scanning recovered hidden letters and tooth counts. Digital models tested ratios. Physical replicas tested movement. Statistical analysis extracted a probable calendar division from a broken arc. Yet, every advance also overturned some earlier confidence. 7. The mechanism is therefore not a relic that finished telling its story. It is a continuing test of how knowledge is built from incomplete evidence. Return to the object in the museum. Irregular green fragments, warped plates, incomplete circles, and teeth. Frozen inside corrosion. Nothing about their appearance resembles the polished reconstructions that now circulate around the world. The complete cosmos exists only where surviving metal, ancient text, astronomy, and modern inference overlap. That may be the mechanism's deepest lesson. Technological history is not a smooth staircase in which every generation keeps everything the previous one knew. Skills can become concentrated, fragile, and dependent on institutions. A masterpiece can survive while the names, tools, and training system that produced it disappear. The gear Valerio's stays noticed in 1902 did not reveal a machine from outside history. It opened a narrow Window into a part of history that had almost vanished. The final unanswered question is not whether ancient people were capable of surprising us. The fragments have already answered that. The question is how many other complex traditions have disappeared so completely that no shipwreck preserved even one example for us to recognize.